Welcome back, Focus Learners. I'm absolutely thrilled to have you here for another explainer. Today, we're tackling a beast that honestly strikes fear into the hearts of a lot of math students. Chapter 2 of Class 12 Maths, Inverse Trigonometric Functions. I know. Whenever the word trigonometry pops up, it usually brings a little bit of anxiety with it. But listen, I promise you, by the end of this explainer, you're not going to feel that way at all. We are going to completely demystify this chapter. We're turning these intimidating concepts into a highly organized, super easy to navigate system of rules and, honestly, cheat codes. Plus, I've got a very special study surprise waiting for you at the end of our session. So grab your notebooks and let's get into it.
Here is our game plan for today. We'll hit 1, the new face of trigonometry, 2, the secret of domain and range, 3, family A and family B, 4, the magic rules of substitution, and wrap up with 5, that special surprise for you.
All right, starting off with Section 1, the new face of trigonometry, turning functions upside down.
So before we do anything crazy, let's just ask ourselves the fundamental question. What does inverse actually mean here? How do we take a standard, normal function that we've known for years and invert it? Well, in the simplest terms, finding an inverse means doing exactly what the word suggests, going backward. It's basically hitting the mathematical rewind button.
Now, how do we represent this rewind mathematically? Over on the left, you've got your standard friends, sine of x, cosine of x. To turn them into an inverse, we use what looks like a reciprocal action, represented by a power of -1. So on the right, sine of x transforms into sine to the power of -1 of x. We read that as inverse sine of x, or arcsine. That tiny little -1 exponent, that's your visual trigger that we've crossed over into inverse territory.
But here is the absolutely crucial point. What happens to the actual data when we apply that -1 exponent? Well, for a normal function like sine of x, the x-axis gives us our input, which is our domain, and the y-axis gives us our output, which is our range. When we create an inverse function, they trade places. The original input becomes our brand new range, and the original output becomes the new domain. It's a complete swap, literally turning the function on its head.
Which brings us to Section 2, the secret of domain and range, solving the one-to-one problem.
Flipping these functions reveals a massive mathematical roadblock. Picture a standard sine wave on a graph. It goes up and down, right? Forever. This means multiple different inputs, like -π/2 and +π/2, can give us repeating outputs. But remember the golden rule of inverse functions from Chapter 1? A function must be one-to-one to be inverted. Every single input has to have one completely unique image. Standard trig functions totally break this rule. They cannot just be naturally inverted as they are. No way.
So how do we fix a repeating wave? Easy. We chop it. We restrict the domain to very specific designated sections, and we call these principal value branches. By carefully cutting off all those repeating parts, we're left with a narrow window where every single input has a unique output. We've essentially forced the function to be one-to-one, which means an inverse can finally exist. It's a really brilliant workaround.
By restricting the sine function to its principal value branch, we get this absolutely essential table. Take a look at the inverse sine function here. Because standard sine outputs values between -1 and 1, our inverse sines domain locks in tightly from -1 to 1. And our new range? It's restricted precisely from -π/2 to π/2. Notice those square brackets? Those are closed intervals, meaning -π/2 and π/2 are strictly included. You're definitely going to want to burn these boundaries into your memory.
Moving right along to Section 3, Family A and Family B, the memorization cheat codes. Staring at a massive table of 6 different inverse trig ranges can feel totally overwhelming, so I'm going to teach you a chunking framework to make memorizing this feel absolutely effortless. Let's dive into Family A. This family is a specific group of 3 functions, inverse sine, inverse cosecant, and inverse tangent. Why group them? Because they all share remarkably similar properties. Their principal value branch ranges are all fundamentally tied to that -π/2 to π/2 block. Sure, there are tiny tweaks, like cosecant skipping 0, but their DNA is all rooted in that exact same negative to positive 90-degree window. And on the other side of town, we have Family B. This family includes inverse cosine, inverse secant, and inverse cotangent. Just like Family A, these 3 behave very similarly to each other. But instead of crossing from negative to positive, Family B draws all of its ranges from 0 to pi.
Again, minor exclusions apply depending on the function, but grouping them mentally as the 0 to pi family is going to save you so much memorization time.
Now here is the ultimate cheat code that makes dividing these families so powerful, the negative angle rules. Look how beautifully this works. If you have a negative input inside your function, family A simply pulls the minus sign straight out to the front. Inverse sine of minus x just becomes minus inverse sine of x. Simple, right? But family B, well, because their range is strictly from 0 to pi, if you have a negative input, family B forces you to subtract the standard function from pi. Inverse cosine of minus x becomes pi minus inverse cosine of x. Memorize this one piece of logic, and honestly, you've already conquered half the chapter.
Let's level up. Section 4. The magic rules of substitution. Unlocking algebraic puzzles. Often, you're going to face some pretty complex algebraic expressions hiding inside these inverse trig functions, and you have to simplify them. How? By substituting that messy algebra with clean, simple trigonometry. The trick is pattern recognition. Look at step 1. If you see the structure a squared plus x squared, your brain should instantly scream, substitute x with a tan theta or a cot theta. It perfectly aligns with standard trig identities to simplify the whole mess. Move to step 2. If you see a squared minus x squared, you immediately swap out the x for a sine theta or a cosine theta. It's like fitting puzzle pieces together.
And when the algebra gets a bit trickier, we just pull out the advanced rules. Look at the top row. It's similar to the last one, but reversed, x squared minus a squared. When you spot this exact structure, you drop in an a secant theta or an a cosecant theta. And look at the bottom row. When you see that daunting square root of a minus x over a plus x, actually scratch that. It's not daunting if you know the trick. You just use an incredibly powerful substitution. X equals a cosine 2 theta. These substitutions instantly collapse complex fractions into clean, solvable terms. It's literally magic.
And finally, Section 5, a special surprise for you, your ultimate toolkit.
You've navigated the conceptual foundations, conquered domain and range, grouped the families, and unlocked the magic substitution codes. I know keeping track of all these brackets and rules can feel like a lot to juggle. That's exactly why I've created a completely free, highly comprehensive PDF formula sheet. It has every single Class 11 identity you might have forgotten, plus every Class 12 inverse rule we covered today. I stayed up late putting this together so you never have to scramble for a formula again. The link is waiting for you in the description right now. Go download it, print it out, and share it with your friends.
So, with the visual concepts from this explainer locked in your mind, and your new master formula sheet printed out, you are officially armed and dangerous. The foundation is rock solid. The only question left is, are you ready to go out there, apply these cheat codes, and completely conquer exercise 2.1? Beyond just this math test, remember that by mastering inversions, you're really learning how to reverse engineer reality itself, taking any outcome and flawlessly tracing it back to its origin. So, what's stopping you? Happy studying, and I'll see you in the next explainer.